Now, this will be a fairly short video. We'll discuss what an inverse hyperbolic function is, but you don't really need to know this at this level, honestly, unless you're from some country that really teaches advanced stuff at a very low level. I don't know. But let's see. Basically, the inverse hyperbolic functions are expressed in terms of natural logarithms, right? So basically, ln, like we discussed earlier, ln being ln x, the natural logarithm of x is basically the logarithm base e of x, right? So the inverse hyperbolic functions are expressed in natural logarithms, and again, like I just said earlier, we shall just study them in higher classes, honestly. But just a brief overview of what it is. Here, you have sine hyperbolic inverse of x. That is the natural logarithm of x plus under root x squared plus 1, right? And the domain of this function is all real numbers, right? Now, cos hyperbolic inverse of x, the difference, again, as you remember, in the normal hyperbolic functions, the difference between the sine hyperbolic function and the cos hyperbolic function was just a single addition and subtraction sign. Similarly here, you have this positive sign in the sine hyperbolic inverse function and this negative sign in the cos hyperbolic inverse function. And otherwise, it's the same. But because of this negative sign here, there is a condition that says that x must be greater than or equal to 1. And the only reason for that is because it cannot have a negative number under this under root sign, right? Because you cannot take the under root of a negative sign, because that will become an imaginary number, and we're not dealing with those, honestly. So yeah, that's why the domain is all numbers, all real numbers greater than or equal to 1. Now, tan hyperbolic inverse of x, as you might have guessed by now, it just is something like this, right? And basically, you'll have to memorize a lot of this stuff. But let's talk about the domain of this particular case. Now, the domain states that you can, for a natural logarithm, you must have a certain value here, and that value must never be basically equal to 0. It must always be greater than 0, which is why you see this denominator here. The first thing is that the denominator must not be equal to 0, right? And that will be equal to 0 if this x is equal to 1. So we've got that cleared out. But this entire function, this entire thing must not be equal to 1 either, because as we discussed earlier, that for the logarithmic functions, the value of x, the value of basically this function inside the logarithm, let's not say x, let's say that if you have ln of, say, a, and a is a function, a is an input variable, the condition here is that a must be greater than 0 and a must not be equal to 1. And over here, you must fulfill that condition on this entire term, 1 plus x over 1 minus x. And these two conditions can only be fulfilled if the absolute value of x is less than 1. So basically, this states that x must be greater than negative 1 and must be less than 1. Okay? So, yeah. This is basically the 3 inverse hyperbolic functions. And you have these 3 as well, which are basically the reciprocals of the previous ones. Cotangent hyperbolic inverse of x is, again, the reciprocal of the tangent hyperbolic inverse function. And again, you'll just have to memorize a lot of this stuff. Secant hyperbolic inverse of x is like this, and the cosecant hyperbolic inverse of x is like this. And these calculations are a bit too tricky, but again, remember that the conditions in the function inside of the natural logarithm, you must fulfill the conditions to get the domain. And in this case, it's the absolute value of x is less than 1. In this case, the secant hyperbolic inverse of x, this is the domain, x is greater than 0 and less than or equal to 1. And in this case, the cosecant hyperbolic inverse of x must not be equal to 0. Simple. Okay? And you can verify this by actually plugging them in here, because let's take cosecant hyperbolic inverse of x. If you plug in x is equal to 0, this term becomes 0, and hence you just know that it becomes undefined. And over here as well, see, you have this x absolute in the denominator, so this becomes undefined as well. Other than that, if you plug in any number over here, in this case it's x squared, so any negative number of x will become positive as well, so you can take the under root and eventually you can calculate the natural logarithm, right? So verify all of these and you get it.